to what? 1 over volume. That's if you are asked to draw the diagram of Boyle's law. Now, if you also want to draw the diagram of Boyle's law this way, you can draw it this way by saying your P is directly proportional to your V, but in a slant direction, meaning that the higher your P, the lower your V. Sure, you understand now. So this will be Px, or let me say Py, Px. So any of these two can represent the graphical representation of your Boyle's law. Now, under our Charles law, know that Charles law states that the volume of a given mass of a gas is directly proportional to its absolute temperature T, provided that the pressure remains constant. What are we saying? Your V is directly proportional to your T, meaning that your V over T equals to a constant. So which now equals to your V1 T1 equals your V2 T2. So this is the fundamental equation of your what? Charles law. So application number 1 for absolute zero of temperature. Charles law shows that if we plot the volume of a given mass of any gas at constant pressure against the temperature, if A and B is produced backward, it means the what? Temperature axis at what? Minus 273 degrees Celsius. What does that mean? Look at. Are we seeing it? So the diagram is going to go this way. Now at this region is where you're going to have your minus 273 degrees Celsius. This is just the illustration of Charles law. This one is measured in what? Meter cube, and this one is measured in what? Degrees Celsius. So that's just the diagram that is explaining your Charles law. But in this, at this region, this particular region where the temperature is being measured as minus 273 degrees Celsius is what we call the absolute zero. If you look at the explanation there, the temperature is called the absolute zero. This shows that temperature is reduced and the volume continues to what? Diminished. Are you seeing it? The temperature is reduced and the volume continues to what? Diminish. Meaning that the volume will only be zero at what? Minus 273 degrees Celsius. Now, cubic expansion of gas. Delta is as a result of the Charles law, and the cubic expansion of gas at constant pressure is defined. You understand? You need to get this one too straight. Cubic expansion of gas as a what? Increase in volume. You know, under linear expansivity. I think we've done this in our SS1 series. Increase in volume over what? Original volume into what? Temperature rise. Multiplied by temperature rise. Now, pressure law or Gay-Lussac's law. Gay-Lussac's law states that the pressure of a given mass of a gas is directly proportional to its absolute temperature, provided that the word volume is constant. P is directly proportional to what? To T. So from there, your P equals KT. Are we saying it? So from there, you'll be able to have your P1 T1 equals your P2 T2. So from there, you have your pressure law equation. So if we proceed, we'll be able to have the general gas equation. That general gas equation is given like this: P1 V1 over T1 equals P2 V2 over what? T2. That's the general gas equation. So if you are to make use of any of them, either your pressure law, general gas equation, Charles law, or your Boyle's law, those are 4 good equations as regards your general gas laws. So let's look at some of the exercises. The absolute zero of temperature is, it should be A. That's your minus 273 degrees Celsius. Now for the second question, it says that the volume of a given mass of gas is this. Now it's 273 at 0 degree. What is the volume at 273 if the pressure remains constant? The volume of a given mass of gas is this at 0. 273 cm cube. Abi? Then I say, what's the volume at 273 degrees Celsius? Okay, 273 degrees Celsius. If pressure remains constant, what do? You just say, okay, your V1 is what? 273. Your T1 is what? 0 degrees Celsius. Your T2 is 273 degrees Celsius. Abi? So we are looking for our what? Our V2. Mind you, if you want to solve any of this equation, you must learn to convert your degree Celsius to what? Kelvin. For the T1 now, which is 0 degrees Celsius, you plus it by 273. That gives you 273 Kelvin. That's your T1. For your T2, which is 273, you just add it to 273. So that gives you 6, 14, carry 1, 4, 5 Kelvin. So these are T2. So we know that our V1 over T1 equals V2 over T2. So if you come up here, you have what are we looking for? We're looking for V2. So we have our V2 to be equals to V1 T2 all over T1. So our V1 is what? 273 times T2, 546 all over T1. What's T1? 273. Right? So from here, you cancel these two. So our V2 is going to give you 546 cm cubed. So that will be our second volume. So let's move into wave. So at this junction now, we're looking at what wave actually is, what is being the two major classes of wave. We're looking at what we call the mechanical wave and electromagnetic wave. Now, also we'll be looking at what is meant by wave motion. After which we'll be looking at transverse and longitudinal wave, the general representation of wave, and so on. So let's proceed. First, we're going to look at waves. Let's look at what wave actually entails. Look at this. If a stone is dropped into a bowl of water, you definitely see ripples or waves are being seen to spread out on the surface of that water from the point where the stone actually dropped. Good. Now, what is wave now? A wave is a disturbance which travels through a medium and transfers energy from one point to another without causing any permanent displacement of the medium itself. Are we getting it? It transfers energy from one point A to point B. It transfers energy from one point to another without causing any deformation. Shall you understand? Any deformation to the what? To the conveying medium. To the medium that is what? Actually accommodating the wave. So that is what a wave is. A disturbance which travels from one point to another. So which travels through a medium and transfers energy from one point to another without causing any permanent displacement of the medium itself. Now this is just a movement or transfer of energy without the system moving itself. Are you getting it now? So without wasting much of our time, we're looking at the two major types of wave. We have what we call the mechanical wave, and two, we have what we call the electromagnetic waves. Let's start with mechanical wave. For the mechanical wave, now this is a type of wave which really do require a material. Do you understand? For its propagation, such as what? Water wave. What does that mean? If I try to drop this stone now in this bowl of water, it goes down, it makes a sound, and it brings out the ripples. Now you realize that this stone is the material used. You understand? So this type of wave created here is a mechanical wave. Why? Because the wave is actually being caused by a what? Material. It is because of the what? Presence of that material that brought about the what? The ripples that has been formed at the surface of that water. Under the electromagnetic, it says this is a type of wave we do not need any material to propagate, for its propagation. That is, the movement of the wave, the movement of the transfer of the disturbance does not need any material. E.g., we have what we call radio wave. You have what we call your radio wave. And most times, this type of wave is what? Invisible. We have what we call X-ray. Most times, The wave flows, but it flows in an invisible manner. You can't see it with your naked eyes. You understand? There are a lot of waves, movement of waves all around. You can see our GSM mast that is being installed at almost every location where you go to. They are what? Emitting so many of waves. They are emitting a lot of radio waves and what? Electromagnetic waves. I mean, radio waves and we have what we call gamma rays. They are emitting a lot, but you can't see those waves movement with your naked eyes. And you can see that those waves will just leave from location or from one point and move to the atmosphere without any material being used for the propagation of the wave movement. So that is the difference between your mechanical wave and your electromagnetic wave. We have what we call wave motion. Now, at this junction, let's take for instance a medium which transfer energy to and fro or vibrate around a mean position as wave passes. Now, the vibration was passed on from one particle of the medium to the next. The direction of the movement of these waves really matters, and the full description will be done in the course of our discussion. You can see those are the little explanation when it comes to wave motion. Now let's go to another two major categories. We'll be looking at what is meant by transverse wave and what is meant by longitudinal wave. Now, depending on the direction of particles of vibration with respect to the direction of the travel of wave, we can distinguish two types of wave. You know, we are looking at the two types now based on the direction. If you are looking at two types based on their properties, we'll be talking about your electromagnetic and your mechanical wave. But here, these two types are based on the direction of movement. So you can be asked in your O-level SSC exam, name the two categories of wave with respect to their properties. You may say mechanical and electromagnetic, but two categories of wave with respect to the direction of movement.